What I'm going to talk about now is the low energy part of the spectrum. And this is a very rich but incredibly complicated part of the spectrum. Everyone thinks that they're going to use it. I've noticed that people tend to use it once and then swear never to use it again. So I want to give you an idea of some of the complexities and challenges involved with this. There are some very useful things you can do. Some are very easy and some are very hard. And what I hope you get out of this is a feeling of why the things that are hard, so that your advisor doesn't sort of push you into doing this and drives you crazy. So the starting point of why do we get attracted to the valence region over here is our core loss excitations are very, very weak. If you look at the oxygen edge, I'm using about 1 in 10,000 electrons is ending up in that edge. So incredibly dose inefficient. And if my material is radiation sensitive, starting out with a process that only uses 1 in 10,000 electrons, you're not on a good footing to begin with, right? So the nice thing about the valence region is this is looking like that's about 10% of my scattering is going into that region. So it's a nice big signal. I can get that signal very quickly, and it's going to be very dose efficient. That's the good news. The bad news is it's a lot of my signal. There's a lot of scattering going on there, and that makes life very, very difficult. So this is a little bit of the simplest thing we can do with the valence region of the spectrum, this peak over here. I'm going to look at this in more detail because the valence region it's called that because it's the excitation of the valence electrons. So I'm exciting electrons in the filled states of the valence band and exciting them to the empty states of the conduction band. And it turns out there are many types of excitations that happen in that range. There's certainly the single particle excitations that are the optical transitions. So we can do optical spectroscopy with this method. But there are also collective excitations where the solid as a whole sloshes around. So this is kind of where you get a sense of how physicists view the world, whereas chemists view the world. Physicists treat everything as a free electron gas. You take all your electrons and you pour it into a big box, and you just calculate the density of those electrons smeared out as if the atoms were just removed into a continuous positive charge background, and the electrons were poured in with the same density. So if you know the density of your solid, then I know the density of my electron gas, and that electron gas sloshes when I hit it with an electron, and the resonance frequency of that electron gas is called the plasma frequency, and we've seen this touched on in several talks before, and it has a very simple formula, and you can derive this with almost a simple harmonic oscillator type expression. The low loss spectrum that you get is proportional to imaginary -1 on epsilon. Epsilon's the frequency-dependent dielectric function. And if I just write this up on the side as a reminder, right, if I wrote this is going to look like, if I worked it out, this would be a epsilon 2 over epsilon 1 squared plus epsilon 2 squared. Remember that if I wrote epsilon is epsilon 1 plus I epsilon 2. This is my complex function over there. And then remember, epsilon 2 is your absorptive part, and epsilon 1 is the reactive or capacitive part. So this is your dielectric screening, and that's the bit that loses energy. So if you look at this formula here, this basically says my loss function should look like an optical loss function with a funny denominator on the bottom. For core loss spectroscopy, so core loss, epsilon 1 is about 1, and epsilon 2 is very, very small. So under those conditions, the loss function is just basically going to be epsilon 2 when I take the imaginary part. So core loss core loss EELS is just approximately going to be epsilon 2. The tricky thing that happens is when epsilon 1 and epsilon 2 are large, then this function has funny shapes. The plasma frequency is the point at which epsilon 1 goes, hits a pole. This whole thing blows up as a denominator, and then you get these lovely sharp peaks. So aluminum, which is a free electron gas, has a beautifully sharp peak at the plasma frequency, and it's nice and narrow. Silicon also has a plasma frequency, and the EELS spectrum is also peaked at the plasma frequency, but it's a little bit broader. And that's a reflection that this collective excitation is a little bit more short-lived because it's decaying into single particle transitions. SiO2 also has a plasma frequency, and you go, wait a minute, SiO2 is not a free electron gas. But if you imagine just displacing all the valence electrons a little bit and letting them slosh around, the lifetime of that free electron excitation is about as long as it takes for an electron to travel to the end of the atom and go, oh, wait a minute, there's nothing there. And then it decays. So the lifetime gets very, very fat. So everything instantaneously for a small perturbation looks like a free electron gas. And then as you let it oscillate in time, if it's a good free electron gas, the oscillation has a good quality factor and therefore a narrow peak. And if it's not a good free electron gas, it has an extremely broad and very, very short lifetime because it's decaying very quickly into single particle excitations. So if you take a look at the experimentally measured plasmon energy and you plot it against the theoretical free electron gas plasmon frequency, most materials fall within a pretty narrow range. It works, and this is from Megan's work, where she was in fact pointing out a whole bunch of liquids also follow the free electron gas model. So we actually put liquids in the electron microscope and hoped that they didn't leak too badly, and measured their plasma frequencies. And it works pretty well. So this is a nice, very quick rule of thumb that you can use to take a guess at the density of a material. It works well for materials that kind of are free electron-ish, and it works very badly for things with tightly bound electrons. So if you actually looked at the optical spectrum of nickel or cobalt or iron, you wouldn't be able to recognize the plasma frequency because there are too many single particle D2F transitions happening in the same energy range. So partially filled DNF shells mess up this analysis completely. And so platinum, people go, hey, platinum is a nice big plasma frequency. It's like, no, that's not a plasma frequency. That's a single particle transition. But for the materials that are not those things, this is a great way to guess the density. This is the biggest scattering you get on the atom anyhow. And so this, in fact, basically, if you know the plasma frequency, you can actually make a guess at the inelastic mean free path. So the formulas used in the Gatan code are assuming a free electron gas to when they magically tell you how thick the sample is. They're telling you how thick the sample is, assuming there are no atoms in there. It all got smeared out. So what we often do with this is most materials, funnily enough, have plasma frequencies about 20 to 25 eV. That's a typical electron density of most things. And there are a couple of elements that fall outside that range. But you can use this change in density. Paolo mentioned that someone actually was trying to measure temperature changes by measuring the shift in the plasma frequency. And that works. The other thing that causes a shift in the plasma frequency is strain. And don't ask me how that can tell temperature changes from strain when you heat up the material and the expansion coefficients of the material change as well. But good luck to them. Here is in the semiconductor industry where we found the plasmon spectroscopy really useful. So silicon has a plasma frequency of 17 electron volts. And you'd get that just by this formula, and you can kind of plug in those numbers very easily. Silicon has 4 valence electrons. You know how many atoms there are per unit volume. As long as you don't get the units wrong, this is easy to do. SiO2 I have to add in a silicon and 2 oxygens, count up the valence electrons, and I only count the valence electrons for the plasma frequency. The core electrons are too tightly bound. You can see here's SiO2 has a plasma frequency of 23 eV. So this is a great way to tell silicon from silicon dioxide in big particles. I'm going to, just a warning, don't do this in tiny things. That's part of the lesson I want to tell you. So here is a material that was grown silicon-rich oxide. So SiOX, it's quite a common material to grow. But if you know the phase diagram of silicon, it wants to phase separate into silicon plus SiO2, the 2 end members. It's not stable as a mixture. And so if you anneal the material, you actually end up with a second peak that pops up over here, because that's the particles that have precipitated out of pure silicon. And then this is sort of the SiO2 matrix. So what you can do, and why you want to do this, is here is a conventional TEM image of silicon-rich silicon oxide. And you can tell there's a bunch of little nanoparticles stuck in there, but there's not a lot of contrast, because by elastic scattering, silicon SiO2, their densities differ by less than 4%. So very, very hard to tell them apart if they're both amorphous. If you use the plasma frequencies, all I have to do to see the silicon is select only the energy losses at 17 eV, and to see the SiO2, I only have to select energy losses at 23 eV. So here we go at 17 eV, and yes, there's a particle. We knew about that one. We knew about that one, but you missed all the ones down there, which were just not oriented on the zone axis. So the plasmon mapping is incredibly valuable for picking up nanoparticles. And we used that to actually do a 3D map. So we used plasmon tomography, right? All we did was we used the energy. We went into TEM mode of the electron microscope. We turned on the imaging filter. We narrowed the slits down to just pick up that energy range. And then we just imaged onto the CCD camera using the energy filter. And then I only got to see the electrons at 17 eV, which got to light up all the silicon particles. And then you just did a tilt series like you did the other day and reconstructed the particles in 3D. That's sort of the best case scenario for which you would be using valence EELS. This is where life is easy. There's a nice big peak. It's cleanly separated. Life is good. It does, actually. If they get too small, you'll get into real trouble. And so I'm going to talk about what happens when they get small. The bigger the nanoparticles, the easier life is. I'll talk about the length scale at which you run into trouble with plasmons. And it's about 2 to 3 nanometers that things start to go very funny. That you shouldn't trust the resolution below a couple of nanometers. Lena touched on this in the previous talk, which is you don't want to do EELS on very thick samples, because multiple scattering of all of those beautiful strong plasmon peaks, each plasmon scatters many, many times, and it washes out all the other details. So remember the mean free path in water. Water had about a 23 eV plasmon energy. And that gives you a mean free path of about 100-ish nanometers, 150 nanometers. You remember exactly? Yeah. So what we have over here is we've made a liquid cell. So we've had 2 silicon nitride windows. We've put water in between the windows. And then we've done EELS by firing the electron beam through this little cell, and it's 2 transparent windows. And this is the EELS spectrum that Megan took of water for a whole bunch of different thicknesses. So you can kind of see over here, this is the thinnest spectrum, and that was 300 nanometers thick, and that's about 3 mean free paths, which means everything is scattered about 3 times. And you can see there's the first plasmon, there's a second plasmon, the third one is already blurred out, because the third plasmon it's a convolution of 3 plasmons, so it has to be 3 times as wide. And then there's the number of peaks follows a Poisson distribution. So there's a whole bunch of things that tail off over there. At 300 nanometers in liquid, you can barely see the oxygen K edge. So core loss spectroscopy in 300 nanometers of liquid would be an incredibly frustrating experience because there's this tiny peak on a big background. You go to 400 nanometers, and I think there's no hope you'd pick up the oxygen signal off that little piece of noise. Or at least people might try that, and then you go, yeah, I think that's just a thickness artifact, because they'd be getting the difference between that shape and that shape. And that's just multiple plasmon scattering. So the problem is, when I get very thick, I can't do core loss spectroscopy anymore. But, and this is a warning. In fact, there's a lot of papers that people have done by liquid cell where they show beautiful oxygen K edges and say, I can do EELS spectroscopy and atomic resolution in liquid. And we go, no, your cell had a leak and all the water came out. And then you look carefully at their oxygen K edge, and you realize it's the oxygen K edge of silicon oxide and not the oxygen K edge of water. They have very different shapes. So there was a paper that was in a microscopy journal, actually won a best paper of the year, because the reviewers were people who didn't know how to look at an EELS spectrum and didn't understand the physics of EELS. So, you know, this is a warning that actually reviewers are people like you, and if they agree to review papers outside their field of expertise, silly things can happen. Now, valence EELS, this region down here. You can kind of look at the spectrum and say, hey, that first peak looks pretty good, even at almost a micron in thickness. Right? And what's going on, and here if I zoom up even closer into this thing over here, this is the optical gap of water, and there's the band edge of water at about 6, 7 eV. And you can kind of see, even here, down to about a micron, you can still tell something about the optical region of the spectrum. It's not great at a micron. It's incredibly noisy, right? It's way, way down in intensity, but there's still something going on there. I wouldn't do it at a micron, but I'd be kind of happy working in those things here up to about half a micron. So the lesson is, if I look at the lowest energy features of my spectrum, there's nothing at lower energy to scatter in and mess up my spectrum, because it's the lowest energy feature. So I can work in really, really thick samples. So that's another advantage of valence EELS over core EELS, is you use it as a last resort when the sample is too thick to do core loss work. Now, what I'd normally say is if the sample is too thick to do core loss work, it probably meant you made a bad sample, and the best thing you can do is go back and make a better sample. But there are cases like it's liquid, and that liquid is bulging out in vacuum, so what are you going to do? That we resort to the valence spectroscopy. So works for thick samples when nothing else works. So that's just reminding us that the core loss spectra, you don't want to be at 300 nanometers. In fact, I wouldn't want to be thicker than 100 nanometers to do core loss work in general, because the beam is going to spread so badly I lost all my spatial resolution. Valence EELS has worse spatial resolution, so we don't care. So this is a little bit of, we've been talking about Poisson distributions all week. Poisson distributions are statistics of scattering. It's basically, if I have, on average, one scattering event on average, and I look at a particular event, what's the odds that I get one scattering event, or two scattering events, or three scattering events? I'm going to come back to this when we start to think about statistics and counting. But this expression should be very familiar to you. How many of you know Beer's law? And for the rest of you, it's the absorption formula that if I shine light into a scattering medium and I look at how much light makes it through the other end, so let's say I have a glass of beer and I shine my laser into the glass of beer, and then all these bubbles knocking light around, the light that comes out the other end, I of t is I0, the incident light, e to the minus t over lambda. That's Beer's law. And it's named for Mr. Beer, not the drink. And if you look at the Poisson distribution and I put n equals 0, then P0 is e to the minus t over lambda. So Beer's law is the probability that we had no scattering in the material. And at one mean free path, the odds that we had no scattering is about 40%. And if I'm at 3 mean free paths, the odds that I had no scattering is about 5%. So it's possible, even in a very thick sample, to get some electrons that make it through without having scattered at all, but that amount is exponentially attenuated. We use that trick a lot in imaging thick samples, that we're looking for a tiny signal on a big background. The single scattering over here is the n equals 1 event. What's the probability I underwent one scattering event? And that's this green curve here. And then all of the multiple scattering events, which is 2 or more events, I've summed them up together to do the red curve. Or more accurately, I think, is that one yours or mine? And this is, in this case, I'm using this to ask how many plasmon scattering events we're getting. And if you think about it, if I want to look at my valence EELS, I want to be tracking and optimizing the single scattering events. So that's the green curve is the bit that I want, and you can kind of see it's doing nicely around about t over lambda is 1. So that would be the sweet spot. You might want to be working thinner than that. You know, over here, the peak to background ratio is really good. So this is kind of where you'd like to be, but you know, hey, we can live with this regime as well. There's still pretty healthy single scattering out here at 3 mean free paths. And then the nice thing is the multiple plasmon scattering is at a higher energy, so it's not going to overlap and mess with our signal. So here we are looking a little bit more carefully. This is a nice example of 2 different liquids, goopy stuff and water. And it's on a log scale, so the plasmon peak over here looks kind of broad. And then you can see there's the optical gap. And what's really nice about this region down here is it's a minimum. There's very little scattering over here. And so if I'm actually looking at liquids and I'm looking at insulators with large band gaps, any kind of optical excitation that fall in this band gap is very, very favorable for studying bivalence EELS, because there's no background to it, whereas everywhere else it's a mess. And so this is, again, just going through this, you know, if I'm willing to look for a signal that's 1% of my background or 1% of my incident beam, the 1% range is up to t over lambda is about 6, which is sort of, you know, it's starting to look like stuff down there. So I'm not necessarily recommending you rush out and go look at micron thick samples. But if you had a micron thick sample, you'd still be able to make some guesses of what some of its properties were. So one of the things you can do with EELS is you can look at the optical gap of materials, right? So what's happening over there is if I draw the band structure of the material, here's all my filled states, here's all my empty states. If I excite electrons from filled to empty states like that, that's basically the same thing as you get with an optical transition if you shone light on the material. And so what I'm going to get to see, if I'm lucky, is this energy here is the band gap, E gap. And in my energy EELS spectrum, there is no energy loss mechanism when the energy loss is smaller than the band gap, because I can't take an electron from a filled state and put it in an empty state. So my energy loss spectrum looks like nothing, nothing, nothing. I hit the band gap, boom, and some shape comes up. And so you can then use that to measure the optical gap in the material. And here are those little inflection points are the optical gaps in these different materials. And then you go look it up, and we measure it by EELS. and then you do your UV vis optical spectroscopy, and the numbers are pretty similar. The EELS doesn't have great energy resolution unless you turn on the monochromator, and so the errors over here, some of these are a little bit big because it's a little hard to figure out where the actual edge ends up. And it turns out optical spectroscopy has exactly the same problem. Half the time we've tried to track down where discrepancies were in solids between our optical spectra and EELS spectra, and it turned out the optical spectra had all sorts of defect and junk and states in the gap, and that extrapolated the tail incorrectly. That the analytic form of what happens with an optical gap and trying to find it is actually quite tricky. You do these so-called Tauch plots, and you have to extrapolate lines because the edges are not sharp. So optically, it's a tough thing to do. Quick example, I told you that there's this lovely gap, which is the optical gap, and there's no excitations happening there, so I can look at very thick things. It's very useful for battery work. So lithium iron phosphate is a battery material, and if you take the lithium out of the lithium iron phosphate, it becomes iron phosphate. You get this very, very big empty d orbital, so you're doing basically a D to F transition. And you get this lovely peak that shows up when the material is delithiated. So now what you can do with your valence EELS is I can sit down at a low energy over here in the liquid, and I can start to look for where my material is lithiated and where it's delithiated. Paolo showed you an example where he used the iron edge at 700 EV energy loss. That's a really bad thing to do because it's an incredibly tiny signal, and batteries and battery electrolytes are incredibly radiation sensitive. So by the time you've done that experiment, half the reason you've lost lithium is because you knocked it out with the electron beam. Lithium iron phosphate, you can't go looking for the lithium L edge because the lithium L edge overlaps with the iron M edge. So that, I think, is that's the lithium L edge, and that's the iron M edge, because this one has no lithium in it, and that one has lithium in it. Good luck telling them apart. So if you want to see lithium, that's how you see lithium. So what did we do? We turned on our energy filter, and we picked a narrow energy window of that. And now you've got a contrast mechanism for seeing lithium. You can't see lithium by elastic scattering because it's so light. So that was all the good news about valence EELS. Now we come to all the bad news about valence EELS. So I should, by the way, just mention that if you look up this paper, we have lovely movies of batteries charging and discharging in liquid, live. Okay, so Lena talked about spatial resolution for core loss EELS. And for the core loss EELS, where things are a couple of hundred volts in energy, the spatial resolution went from a few angstroms to below 2 angstroms, and eventually at high enough energies below 1 angstrom. So all very nicely set up for atomic resolution imaging. The bad news for valence EELS is that's not going to happen. You're not going to get atomic resolution out of a plasmon spectrum unless you've made a very big mistake. And we can talk about what those artifacts are, and if you stick around for the workshop, I'm sure we'll talk about those artifacts again when people make those claims again. So here's an example of a material. This is a diamond nanoparticle stuck in a zinc sulfide matrix. Diamond has a plasmon energy of about 34 eV. It has one of the highest electron densities of anything around. Zinc sulfide has about an 18 eV plasmon. So here at 34 eV you see the diamond, and down here you see the zinc sulfide. And here at the interface between the zinc sulfide and the diamond, you see an interface mode. This interface mode is a dielectric excitation. There's not a special magic bonding state that's happening at that interface. It's electronically very boring. This comes about from the dielectric boundary conditions. I'm going to talk about that more in detail. What I want to point out is that this interface mode is actually quite sharp. Right? This is a 20 nanometer scale bar. This interface mode is about a nanometer wide. So when we talk about blurring and inelastic scattering, there's actually a couple of different length scales involved that makes this a little bit tricky. And it's a little dangerous. It's not that everything blurs out to a couple of nanometers because I'm at a low energy loss. No, it gets worse than that. It means that things below, you can calculate sort of an analytic cutoff for what you'd expect your energy resolution to be. And what you'd find is that the full width half maximum is always very small. The 80% radius, which is the tails that Lena talked about, is big. And what happens in valence EELS is if I have any electric field in the tails, they're going to couple and they're going to set up very interesting standing waves and boundary conditions. And all sorts of goofy, complicated things are going to happen. So in core loss EELS, what's nice is I'm only exciting one atom and I weakly excite the neighboring atoms. But because epsilon 1 is 1 and epsilon 2 is tiny, nothing interesting happens. In valence EELS, these things are very big, and you're going to find out that Maxwell's equations have become important, and I'm setting up standing waves and all sorts of very complicated electrostatic boundary conditions that lead to incredibly complicated spectra that make the interpretation of valence spectra much more difficult than the interpretation of core loss spectra. This is just sort of a calculation that tells you there is some very, very high momentum transfer in the low loss EELS, but it's weak, and that tells you there is a high frequency component, and therefore there's a good spatial resolution component to that, in this case about 0.3 angstroms, about 3 angstroms. But there's also features that are happening on much longer length scales, which is what's giving rise to this funny feature at the interface. So this is kind of what I want to touch on now. So this is the normal kind of analytic theory that you would use for estimating a spatial resolution by EELS. And the quick rule of thumb is the characteristic angle over here. Characteristic angle comes from the scattering theory. And if I wrote it out, it would just be theta E is delta E over 2E0. It's a nice dimensionless parameter that describes the typical angle you'll scatter through for an inelastic scattering event with an energy loss delta E and a beam energy E0. And it more or less comes from conservation of momentum in the small angle approximation. So you use that as the angle that sort of characterizes the Lorentzian profile of the scattering. The spatial resolution that you would guess if you're looking at like a 50% or an 80% radius, you would take the scattering angle to the 3/4 power, you times it by the wavelength, you'd put a fudge factor in the front, and that would be an analytic guess, which is being shown over here. And here's a whole bunch of very complicated calculations of the 80% radius, or the 50% radius, I guess. And this is not the 80% radius is telling you basically how far out your tails go. And what you'll sort of see is core loss EELS, the tails are going out, that's 0.1, that's 1 angstrom, this is 2 angstroms. So when I'm a couple of 100-volt energy losses, my tails are quite localized, and it's easy to interpret the EELS. But when I go down below 100 volts, look how my tails are shooting up. Right now, I'm up, this is a nanometer, that's 2 nanometers, that's 3 nanometers. And this is a warning that funny things are going to happen at about in this energy range. And if I go down, I'm going to talk about phonons at the end. Well, when I pick phonons, I keep extrapolating that curve, and then I get in real trouble. Okay, so you're probably wondering, why was I relating my energy loss to dielectric functions? So let me give you a classical picture of EELS. Here is an electron. It's a moving electron, and it has an electric field. So there's my charge, and there's my field lines. And there it is going past a little atom. So imagine, here's my charged particle. My atom is an electron on a spring. right? There's a positive nucleus holding an electron in with a Coulomb potential. So the electron goes past this electron, and what it's going to do is it's going to push the electron away in the atom, and then that electron is going to spring back based on its restoring force. So here is the electric field that this atom feels as my electron goes past it. This is a time-varying electric field. If I now go to a very, very high-energy electron, the electric field pancakes, right? The field lines get compressed thanks to relativity, and the pulse gets even narrower. So this is a really, really, really sharp pulse. At low energies, it's a broad pulse. At high energies, it's a sharp pulse. What is the Fourier transform of a sharp pulse? So think of what would the frequency spectrum be of something that in time had a very, very, very small delta t. It has to have a very large frequency spread, right? Delta E or delta omega delta t is a constant for a Fourier transform. So the electron traveling at high velocities, and our electrons are traveling at high velocities, very, very, very short, sharp knock on an atom. That means when I Fourier transform it, the Fourier transform of this thing on a log scale is a very, very, very broad range of frequencies. So the way to think of my electron is it's a tiny little light source. It's a tiny little X-ray source that is generating broadband X-rays from very, very high spatial, very, very high frequency X-rays all the way down into the far infrared. Now, if you could build a synchrotron source that could sweep that range of frequencies, you would be very, very happy. So we're very, very happy. We can cover much wider energy ranges than you can in a synchrotron. The time delay for that pulse is in fact set by the velocity of the electron and the impact parameter, the distance of how far your electron is from the atom. So this thing, this little v over b over v is going to give me my delta t. When I Fourier transform 1 over delta t as my delta omega. So my frequency cutoff is this thing v over b. And what this tells me is if I want a higher frequency cutoff, I go to a higher energy, or I go to closer to the atom. So we're going to run this one backwards, and what we're going to find out is that rearranging this formula and writing b equals, b goes on that side equals v over omega, this is called Bohr's adiabatic criterion, because Niels Bohr figured it out first. That is a very simple rule of thumb. That's the length scale over which I get to feel an electric field from the atom. And that's the length scale over which I feel the naked, bare electric field of the system. And I'm going to have to solve for distances less than that, I'm going to have to solve Maxwell's equations to figure out the field distribution. For distances bigger than that, my electric field will decay evanescently, and life becomes much, much simpler. Okay, so we have a broadband source of light. And this is called so what happens when I fire an electron past an atom? The electron moved that, caused the atom to wobble and moved the charge in the atom. So I did work on the system. And the work done on the system is sort of going to be like a half epsilon e squared, right? Classically. So the energy loss that I'm going to experience is the work that I did on the system, which is this half epsilon e squared, which is the energy stored in the system. And then my frequency was just the Fourier transform of my pulse. So what I've plotted over here is the shape of the pulse as a function of my probe on either side of a little harmonic oscillator atom kind of thing. And you can see that I've pulled the electric field to the left and to the right. If I'm looking at the electric field sideways, over here, I'm obviously, the electron is pushing the atom, is pushing the electron in the probe is pushing the electron in the atom away from me. On that side, it's pulling it towards me. So I get a little pulse with an opposite sign on either side. This is kind of a nice thing to excite a dipole. And then if I'm doing the longitudinal field, I have the electron here. Before the atom, I'm pushing it away, and after the atom, I'm pushing it back the other way on the other side. So I get two little field pulses that look like this. When I do the Fourier transform of my electric field, I'm going to get a nice, there's my atom coming across. I'm going to get a nice analytic function. This becomes a K0 Bessel function. That becomes a K1 Bessel function. This is all classical, and it's in the 3 nicest chapters in Jackson. These are my 3 favorite chapters. OK, so I did work on the system. It depends on the electric field, and it depends on the dielectric function. So if I ask what does screening inside a solid look like, I'm going to use a 1 on epsilon of omega as a screening function. My bulk plasmon energy loss it's the work done on the system, so I'm going to take the imaginary part of that, and that will be imaginary minus 1 on epsilon gives me my bulk energy loss function. If I put an electron outside the atom, outside a solid, and I ask what happens when I put an electron outside a metal? I polarize the metal, and the way I model that is I create an image charge. Right? So putting an electron outside a metal, there's an image hole, if you like, that pops up in the metal. And then if you solve your dielectric boundary conditions, the energy loss function is going to be related to imaginary. Basically, I'm going to be looking at 1 over epsilon plus 1. And so the condition for the plasmon pole, which is the collective mode, will be when basically I've got epsilon equals minus 1, and then the denominator blows up on me. So there we go. I've got to get this pole to be, that's got to go, at epsilon equals minus 1, this thing goes negative. And that means the surface plasmon has a energy loss frequency not of omega p, but 1 over root 2 omega p. And that's a result of the electrostatic boundary conditions, right? That the plasma frequency in this material is omega p, and you would have got that from doing that. But if an electron is outside the material, I don't excite the bulk plasmon. I'm exciting basically a surface plasmon, which is trying to get this image charge to slosh around. So you can actually write down your dielectric boundary conditions, and you can ask, here are 2 materials. Material B could be vacuum. Material A could be your solid, or these could be silicon and silicon dioxide. And then you write down and you ask, go back to Jackson and solve the boundary conditions for the problem. And the solution you get is, this is the energy loss function. There are 2 terms. This is the energy loss in material B. There's a bulk term here, which will dominate when I'm very far away. And then there is an interface term, which would be, this was the minus 2 over epsilon 1 plus epsilon 2, or 1 when that material was in vacuum. The K0 Bessel function just has this shape over here. And the K0 Bessel function at small distances diverges logarithmically, so it'll cancel with this first term. So the lesson is over here. What happens is, if I'm in the bulk material, I excite a bulk plasmon. As I come up to the interface, I start to excite an interface mode, and that interface mode has a frequency that depends on both dielectric functions. And the function comes up The K0 Bessel function decays exponentially at large distances, and it diverges logarithmically at small distances. That's the shape of this curve. So what I expect is any EELS of an interface comes up from, exponentially, and then it gets really big at the interface. And the problem with this is, notice that in this model, I haven't allowed for any possibility of bonding at the interface. All of these effects I see are based on the different dielectric responses of the two bulk materials. There's no interface information in this at all, at least from a materials perspective. If you're trying to do plasmonics, this is a wonderful plasmonics thing. If you're trying to solve a materials problem, you learn nothing about the interface. That's the number one mistake people make, is they think they're going to do optical spectroscopy of the interface. And what this theory is telling you is it's going to tell you about everything but the interface. Okay, so there's my interface plasmon, and it's going to decay exponentially. There's my bulk plasmon over here, and it also drops off at the interface. So the bulk mode is suppressed near the surface of the particle or at an interface. So let's take a look at this. Here is a piece of silicon, right? There's a nice big piece of silicon. What happened was, this is me as a grad student, we loaded the sample in the microscope and the thin piece broke off. Like, well, I've still got the microscope, I might as well do something with it. So I just put the beam on the sample. There's my bulk plasmon in the bulk of the material. Here I am outside the material, and there's my surface plasmon. Surface plasmon, 1 over root 2 of the bulk frequency. Here it is down in energy by 1 over root 2. And you can see it's coming up exponentially as I approach the interface. So you can still pick up the bulk plasmon 10, 15 nanometers into vacuum. Right? So here I am outside the material, and I'm exciting electrons inside the material because I create an image charge from the polarization with my electron beam, and my electron beam produced this nice electric field, which is long range and stretches out to a distance v over omega. So now we come to the question of, okay, I actually want to go looking for this nice thin interface layer that my advisor told me should be there. Right? So now I have a three-layer dielectric sample, and I want to find the dielectric function of this thin layer in the middle. If this layer is thinner than v over omega, then the bulk plasmon mode for this thin layer is suppressed. Basically just the same theory that we saw there, just done for 3 layers. So I don't get to see bulk modes, and I don't get to see bulk dielectric functions when B is less than v over omega. And you can kind of plug these numbers in. This is still significant at like 50 volts. So if you're chasing down the magnesium edge in the material and your layer was about a nanometer thick, you may not see it. So here's a practical example of this. Here is silicon dioxide. Remember, silicon dioxide has this 23 eV plasmon. Silicon is 17, so they're nicely separated. Here's 10 nanometers of SiO2. Here's 2 nanometers of SiO2. The thing on the top that's not showing up is more silicon. It's amorphous silicon. But remember, I told you amorphous silicon has about the same density as SiO2. Doesn't have good contrast. So let's do EELS, right? Here in the 10 nanometer thick film, there's the silicon plasmon. Over here is the SiO2 plasmon. It shows up nicely. It's a little bit fuzzy at the interface what's going on there. But here, exactly halfway in the middle of the layer, center of the layer, is a nice SiO2 plasmon. Life is good at 10 nanometers. 2 nanometers, where I'm down near v over omega. Here I am in the center of the layer. That's my silicon plasmon. The only thing that's happened is I see a suppressed silicon plasmon. My 23 eV peak hasn't even made it out the gate there, right? So the 2 nanometer thick layer, and 2 nanometers is 20 angstroms. That's a lot of atoms. The plasmon in the valence spectra is completely lost. We're going to hear on the weekend a lot of talk about valence EELS with phonons. Phonons use not 10 eV energy losses. They use 0.1 eV energy losses. V over omega is going to be hundreds of nanometers. You take exactly the same problem, you rescale it, and you say, well, I shouldn't be seeing any phonons in thin films. Or at least you'll see things, but they won't be from the layer you thought they were. Okay. What happens when I make the sample thicker or thinner? So now I'm just looking at different sample thicknesses. And this funny feature here is the interface plasmon. And it actually does depend quite strongly on the sample thickness. Because what I'm doing, the plasmon is a collective excitation. I'm setting up I'm setting up charge oscillations that slosh throughout the whole material. And those charge oscillations are sensitive to the boundary conditions on the material. And that's what you see happening here. They get quite heavily damped out when the top and bottom surfaces start coupling with each other. They're broadening out because I'm forming, in-phase and out-of-phase modes of charge oscillations. So that's quite complicated, and that's a warning. The other one that comes in, and here's some Cherenkov radiation. I'm going to talk about that in a bit. That tends to be really bad news if you want to look at optical properties. Okay, a couple more fun shapes. I can excite, if I have a spherical mode, then I can calculate all the spherical modes that I can excite of charge oscillations of round metal particles. They have analytic solutions. You probably would find them even in something like Jackson. And here are some examples of these spherical modes. You can see, there's a 3 eV, an 8 eV, and a 15 eV. Paolo showed this one earlier. This is a silver nanoparticle plate. And when you solve for the dielectric boundary functions and ask what are the ways charge can slosh in a triangular plate, it can set up all sorts of interesting standing wave modes. And here are spectra that are excited in the middle of the particle. This is what the bulk silver plasmon looks like. But if I'm on the edge of the particle, remember that's going to be like an interface where it's going to go like 1 over root 2. And at an edge, it's even sharper than that, so it drops to like 1 over root 3. These are the EELS spectra that you would expect to see at different parts on the plate. So when I scan around, the modes have some very interesting features to them. Very easy to understand them. These are just the Fabry-Perot echelon modes in a nice big silver resonant cavity, because that's all this thing is. Here's a nice example for a silver nanorod. Jean-Luigi is going to give a talk, I think, on Saturday. And here it is showing just a silver rod, and you get a whole bunch of standing wave modes at different energies. And those are very easy to calculate analytically for a metal rod, right? This is a simple geometry to do pencil and paper and just solve your electrostatic boundary conditions. If you have a more complicated shape, then you want to solve the Maxwell's equations explicitly. There are codes that are designed to do this. Here's one you can download from the web. It's a MATLAB code. And you'll give it the shape, and it'll solve by boundary element method what the plasmon frequencies would be. There are other packages as well. Finite difference time domain is another one we've used when we have to do optical modes. And MEEP is, I think, the one from MIT. So you just pull them off the web and you run them. Maxwell's equations are not mysteries. Tedious, but doable. How am I doing for time, Lena?
You're done.
I'm done.
Oh, wait, 5 minutes?
OK. So very quick warning here. The plasmons and the optical excitations are not the only thing that happens with a fast electron. If my electron is traveling near the speed of light, then I can start to produce all sorts of relativistic shock waves. And Cherenkov radiation is what happens when my electron is moving faster than the speed of light in the material. Right? So basically what's happening is the electron's moving close to the speed of light in vacuum. It enters a material where the dielectric response is much slower. It lags behind. And then I produce a sonic boom of all these little dipoles trying to follow. And the result is I then generate light. So Cherenkov radiation is that blue glow you see in nuclear reactors when high energy electrons go whizzing into water. In a solid material, then my light is confined into a waveguide, right? Your silicon TM sample is now a planar waveguide. And as a result, I don't get just a continuous spectrum of light, which would be the Cherenkov radiation. I actually get a whole bunch of waveguide modes. So this are the waveguide modes of a silicon slab, and that is the calculated Cherenkov radiation profile for an electron going through it. It differs as a function of thickness because you get different waveguide modes. The main lesson I want you to take away from this is the low-loss EELS spectrum of silicon. Can you tell me where the direct band gap of silicon is? Who remembers what is the direct band gap of silicon? So what's the indirect gap of silicon? So indirect gap is 1.12 eV, and that would be somewhere over there. The direct gap of silicon is 3 eV. That's this feature over here. So when the sample is incredibly thin, you don't get a lot of Cherenkov radiation because it's too thin to have a waveguide mode. And so you get to see the direct gap. You get to see the direct gap quite nicely. The indirect gap is a very weak. It's indirect, so it doesn't show up. There are many, many, many papers of people who have said, hey, look, I have seen the indirect gap of silicon. Look, there it is. This is the Cherenkov radiation mode for that thickness of the material. These are all Cherenkov modes. From here on up, these are Cherenkov radiation. And so you kind of look at the person who did this and say, really? Didn't you wonder why the band gap of silicon was moving so much? But this is basically why it's very hard to do optical spectroscopy with EELS, is in most materials the energy of the electron is high enough that you produce Cherenkov radiation. The one exception to this are 2D materials, because they're too thin to support the Cherenkov modes. I'm going to skip all of that. I want to remind you the main take-home lesson that you should have from this morning is V over omega is the distance at which you run into trouble. That features that are smaller than V over omega, you're going to have to do complicated interpretation. So 17 eV plasma, it's a couple of nanometers. Optical things, it's about 100 nanometers. Phonons, it's going to be sometimes even a micron. I'm going to skip all of this. This is just examples of where people have mistaken stuff. I'm not going to talk about phonons because I'm out of time, but Andrei Kravanek is going to talk about it. All I want to point out is interpretation is very difficult because the delocalization is very, very big. So people tend to get that wrong. And I think at that point, all I want to point, these are the take-home things I want you to remember. V over omega. And here are some references. The most comprehensive reference you have for EELS is the book by Ray Edgerton. And that's a compendium of everything. He's not always right, but at least he's complete. So we occasionally have back and forth, and then he corrects it for the next edition. And then I have some other references for different aspects you might want to think about. So I should stop and take a few questions